this entire chapter, a rather long chapter that we started last week and that will span all of last week and this week. It started with an axiomatic definition of integral. So we said for every non-negative extended Borel function f, we could associate a number and with some properties. We just accepted those properties as axiom, that this way of associating a number to a function, it would be monotone, associative, sigma additive, and unitary. Well, it's now time for us to construct such an operator and show that it exists by actually showing what it is and proving that it satisfies those properties. So this is what we'll be doing in this video lecture and in the subsequent video lectures. We start considering a concept that we saw already, but now this will be a central concept in this video lecture, which is a simple function. A simple function, that's a very simple definition. A simple function is a function that is measurable and takes only finitely many values. And we'll define, we forget about the fact that we have an integral, and we're going to define it. Now we're going to define it explicitly, what it is. So a function, if a function is simple, we define its integral like this. If we want to keep something concrete in our minds, we can think what would be, when we were learning calculus or analysis, what would be the analogous would be a function that is constant by parts and does little jumps like this. We define the integral of that function to be the area of this rectangle plus 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 the area of this rectangle. This is how we define integral of functions which are constant by parts, which are like constant functions that take only finitely many values, these values. And here it is the same, except now the measure is abstract. The measure is not just measuring lengths of intervals, it's an abstract measure, but that's the same thing. This is the rectangle, this is the height of the rectangle, and this is the width of the rectangle, if we can make this a metaphor. And as usual, mu of f equal x is just a short way of writing the measure of the set of all lowercase omega, such that f evaluated at that omega gives x. So we define the integral this way. And now let's discuss the properties of this integral defined for this very particular case, this very small set of functions. And to understand these properties, let's find a representation for a simple function. How can we represent a simple function? Well, let's a1 up to an, this finite collection of numbers, denote all the values that f takes. F takes values on this set, and corresponding to this set of numbers, we can find these measurable sets on our sample space, which means elements of the sigma algebra in our sample space, that are exactly defined by as the sets where the function takes those values. And of course, these sets, they form a partition of omega. And to see that, it is just f takes values a1, a2, a3, a4, an, just f takes finitely many values. And here we have our space omega. Then, of course, these determine a partition of omega. We look all the pre-image of a1, it will be all omegas that are mapped to a1. Then we look at the pre-image of a2, it will be all the omegas that are mapped to a2, and so on. So this determines a partition, or said differently, we can determine whether A belongs to a certain set AG simply by looking whether f of omega equals AG or not, AJ. So this forms a partition. This is a fundamental property, that it forms a partition. And we can express f this way. The function f is this linear combination of indicator functions. And indicator functions, they are very nice functions. They are functions that only take value 0 or 1. And to see that, well, you plug in some omega here. How can you plug in some omega here? Well, you plug it in here. These indicators, all of them will be 0 except the one that corresponds, that contains, whose AJ contains omega. For that one, this indicator will give 1. 1 multiplied by AJ will give us AJ. So indeed, f of omega will be equal to AJ if and only if omega is in AJ as expected. So we have this formula for f, which is very convenient. And now let's make one brief remark, which is the previous representation. Again, what is the representation? A1 up to AN being a partition, if we insist that it's a partition, and A1 little lowercase a1 up to AN being distinct. So really there is only one way to choose these sets and these numbers. They have to match like this, of course, such that f will be written as the sum over j of aj, indicator of aj. And there's a unique way to express f like this, meaning there's a unique choice of this n-tuple of numbers and this n-tuple of sets, except for permutations. We can exchange a1 for a2 if we exchange it also down here. We can exchange any 2 or 3 of these as we please. Of course, this just means reordering this sum here. This doesn't change the result when we evaluate to compute f. But except for that, it is unique, which means this really, there's only one way to write, and this is convenient because now we can make definitions of properties of f in terms of this representation of f. And here we do that indeed, knowing that f is written as the sum over j of aj, indicator of aj. And since this representation is unique, so it is a good way to define the integral like this, as the sum over all these little numbers of the measure of the corresponding set. And again, keeping the analogy with the previous picture, if omega was the set of real numbers, then here we just have a function which is continuous by bits. And what we are doing is we're adding these products here. This here is aj, and this here is the measure of aj. The length is the measure of aj, and the interval itself is aj itself. So we're going to prove later on in the sequence, we're going to prove this lemma here, and you may have heard this expression. It's a familiar expression at this point: unitary, monotone, and linear. This is what our integral operator is. It was an axiom so far, but now we're going to prove it. To prove it, this particular case where the integral is really defined this way. Before we prove this lemma, it is interesting to conclude also this video lecture, or more precisely to conclude this first part of this video lecture. It is interesting to remark that we really didn't have a choice on how to define the integral of a simple function. Okay? There is no other operator with these properties. And what do I mean by that? Well, if you try to define integral of simple measurable functions, if you define it in a way that is unitary and linear, we don't even need monotone here, unitary and linear, we have no choice. And let's explain why. If we assume that f is of this form, and we want to compute the integral of f using the fact that the integral is linear, then immediately we have that the integral of f, the mu, it must be, because f is expressed as this linear combinations of indicator functions, then simply by linearity, if we put an integral here, then the integral would appear here, but since the integral is linear, it would appear here. But now we're assuming not only that the integral is linear, but also unitary, and it means here this is nothing but mu of aj. So we really didn't have a choice but to define it this way. I think this is a good point to stop this first part of the video lecture and talk about this lemma in the second part.